Hey, and welcome to second semester physics. You're probably either in physics 202 or 222. We're going to study the same 5 topics here. You can see them laid out there for you. We're going to talk about heat and thermodynamics first, move on to electricity, then magnetism, and those two are related. They are linked together, electricity and magnetism. We'll see how that happens. We'll talk about waves, and then we'll finish up with optics at the end there. I would like you to know that there is an algebra-based version of second semester physics, and we call that 202. And there is also a calculus-based version right there. If you have any questions about that, please email me, write me, talk to me, whatever, and we'll get that straightened out. If you want to go on and be a 4-year engineering student, if you want to be a physics major, if you want to be probably a chemistry major, you need the 222 version. Okay? If you are doing engineering here at Midlands Tech or transferring to a medical program, medical, I don't know which one you really need. Probably either would do. But the real thing would be to check with the school that you are going to in the program that you're going to, and say, would you guys like me to have calculus physics or algebra-based physics? And they'll be able to tell you for sure. Okay? But we can still get you switched from one to the other if you need it. All right? But anyway, there's our 5 topics again. We're going to talk about heat and thermodynamics here in just a second. So, heat and thermodynamics is pretty important. We use this in lots of things that we do. Our automobiles run because of our understanding of thermodynamics. Our houses are kept hot or cold. There's just so many things that come about. Refrigerators, air conditioning, golly, everything. Balloons blowing up and then expanding and stuff. Just lots of neat stuff here. So this is kind of fun to do. Kind of fun to think about. The first thing I'd really like you to have a clear picture of would be the way that matter works. Sometimes people say that physics is the study of matter and energy. Well, when we talk about matter, we're talking about kind of 3 different states of matter. And the first possibility is that this matter is a solid. The second, that it's a liquid, and the third, that it's a gas. And so here I've got all 3 of those here. In the first one you can see matter as a solid. If you would imagine an ice cube for me, then it's just a nice little block of molecules that are stuck together. They have taken that shape. They have that fixed volume and shape. It's rigid. You can't compress an ice cube like a marshmallow or something. The particles are pretty close together. They do not flow easily. If you could zoom in on them, they would be wiggling ever so slightly. All right. Going to the next picture, liquids. They take the shape of the container. So if you put an ice cube in a glass and it melts, then that water, those water molecules will expand to fill the bottom of the cup. Particles move rapidly, but they slide over each other. You can't really compress water, but it does flow easily. And then lastly, gases take the shape or the volume of the container, and there it's not the bottom of the container, it's the entire container. So if I close some gas up in a Ziploc bag or a Tupperware box or whatever, those molecules are trapped in there, and they're going to evenly spread themselves out. The particles are far apart. There's lots of space in between them. They are relatively small compared to the space between them. They move at high speeds. We'll actually calculate that speed before this is over with. They're in constant collision with both each other and with the walls of the container. Gas is compressible, so you could mash it down. Essentially what you're doing is you're just packing the molecules closer together such that that air, that space between them is pressed out. and they also flow very easily. Now I've got this little animation I'd like you to take a look at here, because I really want you to have this picture in your head. This comes from a site that we'll be using some here, and what you see is a block of water molecules. Remember, water is two hydrogens bonded onto an oxygen. So you see that red oxygen and the two hydrogens tied on there. And even though this is ice, even though this is a solid, if you could zoom in with a microscope, you would see them kind of jiggling about like that. They still have some energy. I'm going to flip over here to neon real quick, because that makes a nicer cube. And maybe that's a better picture to think about with water. There's our block of ice, our ice cube sitting there in the thing. If I click liquid, then you can see that that block has melted, and those molecules have assumed the shape of the bottom of the cup. They just kind of fill the bottom of the cup. You've got one or two that are kind of floating around. These guys, again, have energy. Did you see that collision there? There's a collision. They're bumping into each other. They're bumping off of the walls, off the bottom, and they're just going crazy in there. Here's a gas version like that. So that's a kind of a good picture to keep in your mind. Let me go back to the solid. I'm going to turn the burner on underneath this thing, and you can see here that as I added heat, those things begin to vibrate more. They begin to move more. And they're flowing down into the bottom of the cup. That ice is melting. Let me give it a little bit more heat there. And now we've changed that solid into the liquid by adding heat. The temperature up here also shows that it went up, I think, from 14 to we're 29 now. And you've got most of it liquid. Some of it's up here in the gas state. And but if we continue to add heat, at some point, all those molecules will have enough energy, and you see the more energetic ones bounce into the slower ones and kind of get everybody moving more or less the same. All right, so that's kind of an interesting picture, an interesting thought. Switching back to water here, here's that solid, and I add some heat, and you can see these guys just start to kind of go crazy there. They're really doing two things. They're kind of moving in space. That's a translational motion, and they have translational kinetic energy, but they also have that rotational kinetic energy. We couldn't really see that with the neon, but these guys are just spinning and they're moving around in space. Here they go into the liquid state, 399 Kelvin. We're about to talk about the temperature, and we've got some going up into a gas there. And we'll just heat them up real good here. And those guys are going to scatter all over the place. But again, they're spinning and moving. So there's two kinds of energy there. There's actually also a third kind of vibrational, where that oxygen in the middle and the hydrogens kind of bounce back and forth around the hydrogen. Very, very small, very slight. It's almost like they're on springs, and they just kind of bounce back and forth. Okay? But keep that picture in your mind, and especially as we think about heat and thermodynamics, we're going to talk about calorimetry. How much heat does it take to go from here to here? That's the trick on this thing, that I need to come in here, and we're going to add heat, add energy. Heat is the form that we're putting in, but that's going to take me from a solid to a liquid. And I add some more energy, and it goes from liquid to gas. Of course, we could go the other way. We could remove energy and go from gas to liquid and then down to solid. But that's something we want to talk about here today. All right. Here's some definitions for you. The internal energy is the sum of the kinetic energies of the molecules of matter. So we already talked about that gas molecule or water molecule or even a solid molecule. It doesn't really matter. Here's a molecule. If it's moving, that's kinetic energy. If it's something like water where I can see the shape and it's spinning, that's kinetic energy. We refer to this as translational, and this is rotational. And then also it could be kind of You know, picture this thing on little springs right here. Not a very good spring. But these guys are kind of vibrating back and forth. And so there's also vibrational kinetic energy. And when you add up all the kinetic energy of all the molecules that are in the sample, then that's what we call the internal energy. All right. Heat is internal energy in transit. You probably know that heat always goes from hot to cold unless we force it to go backwards. And we call that refrigeration or air conditioning or something. But in nature, heat always flows from a hot object to a cold object, never from a cold object to a hot object. The temperature is the measure of the average kinetic energy of molecules. So when we're thinking about these molecules that are jumping around, the temperature is a way to say, on average, a molecule in this sample has this much kinetic energy. Okay? And a thermometer, of course, is the device to measure that kinetic energy. So it all comes back to energy. Physics is the study of matter and energy. Here are some different ways to measure temperature. I don't think there'd be any real surprises here. This is probably what we're most used to right here. An old glass thermometer. It has mercury or alcohol, some kind of liquid in it, and the bulb here, you know, kind of holds that reservoir. But as it gets hotter during the day, let's say, or if you put this thing under your tongue or something, then heat is going to move from hot to cold, from your tongue to the liquid in the thermometer, from the temperature outside to the thermometer. And that temperature, that heat, is going to make these things vibrate more rapidly, and they need a little bit more room, and they expand. So this thing may rise on up, and we get a new temperature. Okay? Right here I've got a digital thermometer. There's a little metal thing down here at the end. The heat is going to go onto that. There is a little resistor called a thermistor, whose value of resistance changes with temperature, and they can put a voltage across that and read the drop and use a scale, linear scale, to put the temperature up here. So that's kind of a handy thing. Right here you've got an old bimetallic strip. You can look up that if you're interested. We don't use these a whole lot anymore. When I was a kid, all the thermostats for furnaces and stuff had a bimetallic strip like this in it. You got two different kinds of metal. This one's brass and steel, and those are going to expand at different rates as they go from one temperature to another. They get bigger, but one of them gets bigger more than the other one. And here brass is going to expand more than the other, and that's going to bend this thing that way, and a little needle here would point from 1 degree to another degree or something. Okay, so that's a bimetallic strip. That's interesting stuff. I've got some in lab. If we ever get to meet again, I'll show you those. Right here, this is called a Newton's thermometer or something like that. Basically, you've got these little glass balls that float in water, and as the temperature changes in the water, then these glass balls get more or less buoyant. And you remember doing buoyancy problems in Physics 1. You got the weight pulling down, you got the buoyant force up, and you could work that up. But the trick here is that the water's buoyancy changes by temperature. As the density of the water changes, that changes the buoyancy, and so it pushes it up or down. Basically, you just want to pick the one that's kind of floating at the bottom here, this guy, and just read the little tag. That little metal tag right there says 78 degrees, and that's your temperature. All right, so lots of different ways to measure heat or temperature here. They almost all come back to some kind of motion, some kind of change in the density of the liquid in the alcohol. The digital one might be the exception here, but here you're changing the, as it expands, that changes the density of the water. So there's some parallels between all of them there. We use different temperature scales to measure the temperature, right? You did this back in 4th grade or somewhere, so I won't bore you too much with this, I hope. But the main two scales that we use would be Celsius and Fahrenheit. In this country, if you read the weather report, it's going to be in Fahrenheit because we use the backward system, right? Whereas the rest of the world uses the metric system. So this is the metric unit of temperature, degrees Celsius. It's a really nice scale because water freezes at 0 and it boils at 100. What could be easier? You come over here to Fahrenheit and water freezes at 32 and it boils at 212. Who came up with that? Well, I'll tell you who came up with that. It was these guys that were messing around with this weird mix of salt and water, and it froze at a different temperature and boiled at a different temperature and stuff. So they just set up their scale based on that. There's an interesting NOVA show on that if you really want to see the gory details. But here's a couple formulas that are useful if you want the temperature in Fahrenheit. Knowing the temperature in Celsius, then you can just run it through here. And if you know the temperature in Fahrenheit and you want the Celsius, you could do that. So since we need to do some of these, let's try a couple here. And let's say that if the temperature in Celsius is, 40 degrees, find the temperature in Fahrenheit. Okay? So I write down my formula, T sub F equals 9/5 T sub C plus 32. And I want to put that 40 degrees in right here. And you can see I kind of cheated here. 5 is going to go into 48 times. So I kind of rigged that, I guess. That's going to be a 72, 72. And 32 would be 104 degrees Fahrenheit. It's pretty easy to change these things back and forth like that. If you had temperature in Fahrenheit, you could do this and then back up in Celsius. It's not too hard to cook these formulas up. Right here, if you had the temperature, you can do this either way, but let's say in Fahrenheit. And this is the temperature in Celsius, and it might have been easier to do it the other way, but whatever. Here's my freezing point of water, and here is the boiling point of water, and over here I'm looking at 0 and 100. And so 32 matches up with 0 and 212 matches up with 100. I could find the slope of that line, and I could find the y-intercept, and this is just y equals mx plus b right here. And I really should have done it the other way. This would come out right here. So the slope of this line, the one we've got, is 5/9, and then you can see that line is going to come down here and cross at -32, and so you got to account for that and stuff. But you can always get back to these formulas, remembering the water freezing and boiling points is just y equals mx plus b there. So play with that if you want to see how that works out. But I need to tell you about Kelvin too, because we're going to be using that right here. This guy is pretty important in what we do. The temperature in Kelvin. Now this is still metric stuff, and it wouldn't hurt to know that there is a version of this that goes with Fahrenheit called Rankine, like that. We don't need that, but there is a companion. Basically these two go together, and Fahrenheit and Rankine go together. And there are certain problems that you have to do in what's called an absolute temperature scale. And the reason it's called absolute temperature scale is because it goes down to absolute 0. So real quick here, one more graph for you. If I put the temperature in Celsius here, and I graph how much energy these. I'm going to put kinetic energy here because remember those molecules jumping around? That they had kinetic energy. And I'm going to put 2 points on here. I'm just kind of freehanding this, so it's not going to come out real good, but I think you can get the idea if it'll let me draw. All right, tell you what. It's mad because of those letters there, so I'm going to put temperature on the bottom one like we had, but I'm going to put it over here just to make it happy. Temperature in Celsius. And so, no, still not happy. There we go. Here's 0 degrees, and here is 100 degrees. That would be the freezing point and the boiling point of water right there. All right? And then if I come over here and think about how much kinetic energy these guys have, I could draw a line right here that represents how much energy they have when at the freezing point of water, or the melting point of water. And then right here I could have a point that represents how much energy they have at the boiling point. And remember how that energy went up as I added some heat? Then they had more kinetic energy. So more temperature, more energy right there. But if I continue that line down like that, there's this point where theoretically I get to 0. And this isn't a very good graph because it's not anywhere near the scale. But we call that point right there absolute 0. And so when I measure things in the temperature scale starting right there, if I come through and call this 0, oh boy, can't see that. What else we got? How about some, red's fine. So right here, if I'm at 0 Kelvin, that point where all the kinetic energy theoretically stops, then that's our starting point. We're not starting from the melting point of water. We're starting from way down here where everything stops. And the difference, the distance, if you will, right here, that's 273 degrees. So I'd have to shift downwards 273. In Celsius, that would be negative 273. In Kelvin, all we got to do is just add 273, and we end up with a temperature in Kelvin. For the boiling point, I add 273, and I get 373. All right? So there's nothing hard about getting to Kelvin. Once you have the temperature in Celsius, the temperature in Kelvin is equal to the temperature in Celsius plus 273 degrees. Made a big mess there. All right. Thank you. All right. And that will always give us that temperature in Kelvin. You will know when to use the Kelvin scale because the constant has kelvins in it, or because it's something like the ideal gas law where it only works if you do it in Kelvin. Some other places. I'll point those out as we come to them. All right, but those are the scales that we use. Incidentally, if you need to change Fahrenheit to Rankine, you would add 460 degrees to get to Rankine. Changing 273 to Fahrenheit would give you 460. So that's the number that you need there. All right. I've already said a couple times that when you heat things, they get bigger, right? So I'm looking at 3 pictures here. In the first one, I've got a train that is off the tracks because the tracks went wackadoo, because the sun shone down on them and they got really, really hot and they expanded and they didn't leave enough gap in there. And so they had to go somewhere and they just buckled. All right? And the train tracks got wacky and then the train flipped off of the track. That's bad, right? Right here in picture number 2, I've got a brick wall, and you can see this rubber gasket in the middle of it. That is there because when the sun shines on the brick and it gets hot, it's going to expand, and it's got to have somewhere to expand to, so they put that expansion joint in there to give it a little bit of squishy room to get bigger. If you didn't have that in there, the brick would crack, the mortar would crack. Eventually, you know, the structural integrity of the building would be diminished. Right here, I'm looking at a bridge going across, you know, down in Charleston or something, some big bridge, and it's made out of steel. It's a cold day, but then it gets hot. It heated up. It's going to expand. It has to have somewhere to expand. So this expansion joint right there gives it a place to go. And the table is shows the coefficients of thermal expansion. All right, so aluminum is going to expand differently than concrete, different than diamond or glass or water or whatever you put in here. And this number, alpha, right here says how much are you going to expand by? And again, they all expand differently. The units up here are times 10 to the negative 6 per degree Celsius. So it's not a huge amount that we're talking about. That times 10 to the negative 6 is going to knock it down. But let's try a couple of these. I can't remember what's on the next. Yeah, here's an iron bar. Okay, real simple formula. You see it up here at the top. There's nothing too tricky about doing this. It's just multiplying three numbers. But this 4 meters right there is the original length of the bar. And then we're going to heat this thing by 80 degrees Celsius. That's my delta T. And alpha is this constant that just comes off of the table. I don't think they had iron on that table. Let's go back and here's stainless steel. That's pretty close. Stainless steel has got some other stuff mixed in, so it's a little bit different. But you can see it's in the same ballpark, right? Concrete's kind of in the same ballpark, but not aluminum, not water, right? Different things are going to expand differently. We need to know what it is we're talking about. You want to find the change in length. This is super easy. Change in length is equal to alpha L naught delta T. The alpha was 12 times 10 to the negative 6 per degree Celsius. I multiply that by the 4 meters of rod that I started with. And delta T is 80 degrees Celsius. Now you want to always make sure that the units do what they're supposed to do. You could have gotten through Physics 1 not paying much attention to the units, but I invoke upon you the necessity of paying attention to it here. This one works out nice because there's a degree Celsius and here's a degree Celsius. Okay? So I'm going to cancel that out. I'm going to try. My degrees Celsius canceled out. The only unit left is meters. That's nice because we were looking for a change in length, and all we have to do is multiply those three numbers right there. So I'm going to come along and go 12, second comma gives me the EE, negative 6 times 4 times 80, and I get a little bitty number. The change in length is 0.00384. And again, that was in meters. Okay. If I wanted to find the new length of the rod, let's call that L prime maybe. That would be L naught plus delta L, and I had 4 meters plus 0.00384 meters. So we're not talking about a huge change, you know, as far as a percentage of the metal itself, but it's something that builders do need to plan for, right? And any kind of thing, it's a consideration that you have to worry about. All right, so that's pretty easy. If it expands in length, we call it linear expansion. There's also a volumetric expansion. As I heat this cylinder right here, it's going to get wider and taller and deeper and make a bigger cylinder right there. There is a formula right there that looks suspiciously like the first one that we had. So you probably want to jot both of those down somewhere. The only difference is that we're talking about volume. So there's the change in volume, and V naught right there is a beta. So if I go back to that table, the second column has beta right there. We use alpha for the linear expansion, and beta for the volumetric expansion. Right there. Can you see the pattern between here? Let's look at diamond. Alpha is 1, beta is 3. Concrete is 12, beta is 36. They're just 3 times bigger. All right, 9 times 3 is 27. 17 times 3 is 21. In general, beta will be, not always, some materials are kind of weird, but beta is going to be alpha times 3. Okay, in general. So if you don't have beta, you can get it pretty easily. The materials that wouldn't expand uniformly in length, width, and height would be some kind of composite material, some kind of man-made thing. Maybe plywood expands in length and width, but not in height at the same rate or something. So there you'd have a different volumetric expansion, and you'd have to go get that number and stuff. Okay, I don't need you to do that, so don't worry about it. But it looks like that. Right here, we'll do this again, but I don't think there's any real reason to do it. I'll tell you what, I'm going to do an extra thing here. What if it says find the final length? And you can do this with the, not the length, the final volume. You can do it with length or volume. But check this out right here. The final length, we'll call that V prime, is going to be equal to the original length V naught plus the change in length. And up there at the top it says that that is beta V naught delta T. And now you see how I've got a common factor of V naught in there. So if I factor that out front, I could also write this way. And that would be the final length right there. Maybe that's easier, better, whatever. You could always find the change and then I give up. And, you know, just add it to the original. But whatever. It's a nice way to do it. Okay. And I won't even do the numbers on that. You can see where that's going. Let's see. So that's today's little discussion. We'll pick it back up another day. And I've got some more videos for you. Basically, you want to watch the videos, and then there'll be a set of questions that go with it. I call that a LOP, short for learning opportunity. It's kind of like a pop quiz. This is a LOP quiz, learning opportunity. The nice thing about the LOPs is that you can answer these questions and see how you did, and if you don't like your grade, you can come back and do them again. You get up to 3 shots on all the LOPs, and there will always be a LOP that goes with each video. So watch the video and then go answer the questions in the LOP. It's right there in D2L in the content browser. I haven't built all this stuff up yet, but I should have pulled this up so you could see it. But all you got to do is start at the content browser and just fall straight down the list. Just click things off as you come to them. And again, this is kind of all messed up, and I don't know why it's so slow. But here is Physics 222, for example. And if I go to the content browser, I'm recording this video right now, so it's not D2L, but let's pretend that it's right there at the top. So you've got your thermal expansion video, and then right there, the next thing is the thermal expansion LOP. And you answer those questions. You get to do it 3 times. It's going to count the highest attempt as your grade on the LOP. All right? And all you got to do is just work straight down the thing. I'll put the rest of the videos in here. We'll have more LOPs. We've got some labs. Currently, we're doing all those labs at home. Perhaps one day we will get to reconvene and do those in each other's presence. But for the moment, we are doing that at home. When you get down to the bottom, there will be a test, and that'll be test 1 on the heat and thermodynamics stuff. Okay? And then we move on to electricity. So it works like that. You also get 3 attempts on the test. It's actually the average of the 3 test attempts. You don't have to take it but once, but if you take it more than once, it's the average of the test attempts instead of the highest of the LOP attempts. Got it? So just email me any questions you have about how this all works. But this is your best friend right here. When you log into your class, you got that button right there, Content Browser, and you click that and just start at the top and just work your way all the way down. All right. So thank you for your attention and time, and have a good day.